In this video, we're going to learn about another application of the Cauchy-Riemann equations, the harmonic functions. Consider the two-dimensional Laplace equation, which is defined as the del phi. Del is defined as the second partial derivative of phi with respect to x and the second partial derivative of phi with respect to y. So this is what we call the Laplace equation. For a function phi, for a difference function phi, because we want to make sure that this function can be partially differentiated enough. And then we can continue. It says that a real valued function phi is said to be harmonic in D, in a domain D. A domain means an open connected set is called a domain. If all its second partial derivatives are continuous and at each point of D, the domain, a phi satisfies the Laplace equation. Satisfies the Laplace equation when we call it a harmonic functions. Harmonic. So then we have this interesting theorem for harmonic functions, but it says that if you have a analytic function which the u and v as the real and imaginary parts is an analytic in domain D, then each of functions, the real part and the imaginary part, are harmonic in D. That's like a very interesting result. That means if you know that a complex function is analytic in a domain, then the real and imaginary part satisfy the Laplace equation or it be harmonic. So that's like a very important result. And then you can also say that this is like another fact about this. For a given harmonic function u or v, any of them, in an open set G, we can find another harmonic function v such that u plus iv is analytic in G. So that means if you are given a harmonic function in an open set G, we can always find another harmonic function so that the u plus iv is analytic in G. We call that function is the harmonic conjugate of u. Harmonic conjugate of u. So it can be the u or v depending on what is given. Let's look at the proof of the theorem. So again, what the theorem says, if we have an analytic function, the real and imaginary parts are harmonic. So let's see how we can prove this. Actually, we can prove this result using the Cauchy-Riemann equations. Later in this course, actually, we will show that the real and imaginary parts of any analytic function have continuous partial derivatives of any order. So you can go indefinitely. So that's something. So that means if you have an analytic function, the real and imaginary parts have continuous partial derivatives of any order. So we can use this fact. That means in particular, you can say that the mixed partial derivatives are equal. That means this one. So if you change the order, da by squared v over da by u da by x equal da by squared v over da by x da by y. So that they are equal. So that's like a key point here. Now, since fx equal u plus iv is analytic and satisfies the Cauchy-Riemann equations, we know this one. We know the partial derivative of u with respect to x equal partial derivative of v with respect to y. That's the first condition of the Cauchy-Riemann equations. Now what we do, we take another partial x derivative of that equation. So when you do that, you can see you're gonna get this one. You take another one, another partial derivative. But now what we do, we use the result here. So we know that the mixed partial derivatives are equal. So we know that. So this is coming from that. The mixed partial derivatives are equal. So we can switch the order. The first one is coming from the Cauchy-Riemann equation, equation number 1. And then the second one is coming from the continuity result. Now what we're gonna do, we can rewrite this in this form, we can exaggerate, we can pull out da bar over da bar y. Now what we do, we're going to substitute for da bar v over da bar x from the second Cauchy-Riemann equation. So that's the Cauchy-Riemann equation number 2. We're going to substitute for da bar v over da bar x, which is equal to negative da bar u over da bar y. Now what we can do, we can pull the negative sign out and bring both to one side. So this says that the function u is harmonic. So now you can actually show that similarly function v is also harmonic. So you can try that as an exercise. So now let's try to use this idea in problems. So let's look at one of the very interesting problem. So what it says that find an analytic function whose real part is given by this function. So only the real part is given. So the question is, can you find an analytic function whose real part is equals to x cubed minus 3xy squared minus 2y. So what we're going to do, first we're going to check whether this function u is harmonic, because if it is not, then there is no analytic function. So you don't want to waste your time. So we check whether that's the case. So for that, what we do, we take the second partial derivative with respect to x, second partial derivative with respect to y. So we first take the first derivative, first x derivative, and take one more, plus we take the first y derivative and take one more y. And then in the next step, we try to take the another x derivative, you get 6x, another y derivative, you get negative 6x, they cancel out and you get a 0. So this says that yes, it satisfies the Laplace equation. That means it is harmonic. So we know that. So therefore we can, so because of that, then we know that we can find a harmonic conjugate, because we know that it's a harmonic. So that means there is a harmonic conjugate. So let's say that is V, and then such that the fx plus uiv is analytic, because you show that it is harmonic. Now we also know that since f satisfies the Cauchy-Riemann equation, because we know that it's analytic, that means the u and v should satisfy Cauchy-Riemann equations. So that means ux, that means you take the first partial derivative of the given equation, which is 3x squared minus 3y squared, should be equal to Vy, should be equal to Vy. So now what we do, so this is a Vy equation. Now we only consider this part of the equation. We only consider this part of the equation and take a, you integrate with respect to y now. So you take the equation and integrate with respect to y. So when you integrate with respect to y, what happens? So you get v equal 3x squared y. This is remember, it's a partial integration. It's a partial integration. So you get 3x squared y. That means you assume x is a constant, and minus y3. So you get minus y cubed. And then it is not just a constant, because since it's a partial integration, you get a function of x. Plus, I'm going to exaggerate a little. You will see why in a minute. Add a constant also. So it's just a little exaggeration. Now what we do, so we consider the ux equation. We do the same thing with uy equation now, because we really don't know what is hx here. It's a function, that's the only thing we know, but we don't know what the function is. So what we're going to do, we're going to look at the uy equation. So let's do that now. So using the second Cauchy-Riemann equations, you can write uy now. That means you take the y derivative. So into the y derivative, you get negative 6x, negative 2. From the second equation, you know that uy equals to negative vx. Now what we can do, we can solve for vx, and now we take you integrate with respect to x now. So it is the partial integration with respect to x. So when you do that, you get v equal 3x squared plus 2x. Remember, this negative sign is not there because you can cancel negative sign. So you get 3x squared plus y plus 3x plus 2x, and then since this is a partial integration with respect to y, with respect to x, you get a gy term, because there may be a function of y, because when you take the partial derivative, they're going to cancel out. So we don't know, so we just put it there, and again we put another constant there. Now you can see that you have two different expression for the same function. So they should be the same. So that means you can easily find hx and gy from this one. So you can see that hx should be 2x here, and then you can also see that the gy should be negative y cube. So that's you can easily find that. So you get hx equal to x, gy equal negative y cube. So that means finally, because of that, you can write the final v in this form, which is 3x squared y minus y3 plus 2x. For a reason that will be very clear later, we just add a constant, but we just add the constant, not just a, we just say 2a. You will see why you want to do that later. You can just add an a, that's also okay, but you will see if you add 2a, it will simplify really well. So, and that's exactly the function that we are looking for. But we can do a little bit more here. So remember this problem, how we did it, and again, like this is like how you normally solve a exact differential equation. So this is what we normally call the shortcut way to do it. So if you are not familiar with the C, you can see that normally when you do a problem, you take another derivative and you do like multiple things. But we can avoid everything just doing this way. You consider the x equation and the y equation separately. Remember what we did? We integrate with respect to x, and we also integrate y, and we also integrate with respect to x. So and then you get two different expressions, and you can mesh the unknowns. It's like a shortcut way to do it, and you can find a link in the description if you want to know more about this technique. This is a shortcut method for exact equations. Okay, so let's continue. Now since we know the Vx, actually we can write the actual analytic function. So let's do that. So we know fx equal ux, uxy plus vxy. We're going to plug into that. That's the given function. This is a function we found. We plug in there. And then what we do, we collect terms. We collect these three terms, and then we also collect these the I terms separately and real terms separately, imaginary terms separately. And you can clearly see that the first term is the x plus iy cube. The second term you can take 2i out. See the reason why you have to write 2, because you can see you can pull 2 out. So you pull 2i out, and then you can see this x plus iy plus a. So you can finally write it in this form, and you can see that this is a function of z alone. So we talked about this earlier. So if it is an analytic function, you can always write using a function of z alone. That's exactly what we get as expected. So let's look at another problem. So the question is, can there be an analytic function whose real part is given by, again, it can be real or imaginary part, it doesn't really matter. So the question is, can there be an analytic function whose real part is this one? So what we can do, so we really don't know about this one. So what we do, we check the harmonic condition, whether this satisfies the Laplace equation. So let's do that. So if you take so the answer is actually no. But let's see why. So the argument is, if there were an analytic function f, then its real and imaginary part should satisfy the Laplace equation or should be harmonic. That means if you take the partial derivatives and add them, you should get 0. So that means, so you take the second partial derivative here, and again the second partial derivative with respect to y here, and so when you add them, this is what you get, which is equal to negative 2x. So you impose this condition, you set it equal to 0, but you can see that this is not 0 in general. It's not 0 in general. So that means it is only 0. It's only valid on the line x equals 0. X is the real part, equals 0, but not in any open disk. So what does that mean? So you can see that it is 0 only on this line where x equals 0, x coordinate 0. That's x equals 0 line. Because if you draw any open disk, any point, pick a point, and if you draw any open disk, and you can see that there are parts outside of this one. So that means you cannot find any open disk here. So thus you can see that there cannot be analytic. So f cannot be analytic. So therefore such f does not exist. So let's learn something interesting about the harmonic conjugates. So what it says that the harmonic functions forming the real and imaginary part of a analytic function fc, which is u plus iv, each generates a what we call a family of curves in the xy plane. These are called level curves, or in other words isotemic curves, and are produced by these two equations. So you get the real part, set it equal to 0. That's how you get level curves depending on the value you pick. And you can also find level curves for v, level curves for u, and level curves for v. So for example, if you represent temperature, then the these curves, the level curves are isotherms. And then also this is very useful in electricity, like if you have like a charge, then if you have electrostatic field, and you can see that these are potential curves, equipotential curves. So there's a lot of application in this one. So let's look at this problem now. So what it says that for the analytic function, z squared, which is equals to x squared minus y squared plus I times 2xy, the level curves are given by one set is u, which is x squared minus y squared, a constant, are the hyperbolas with asymptotes y equal plus or minus x. We know that, we learn in Calc 3. While the level curves for the other one, v equal 2xy constant, are again what we normally call rectangular hyperbolas with coordinate axis as asymptotes. For the second one, those are coordinate axis, and you can see them, like if you graph them, the first one on the left are the level curves of u, and the one on the right are the level curves of v. The interesting thing is, if you put them together in the same graph, and you can see that these graphs actually cross at 90 degree. So they intersect at 90 degree. So this is actually interesting fact about level curves of conjugate pairs. So let's try to prove this result. We're going to prove this result. That's an interesting result. What it says that the level curves of the real and imaginary parts of an analytic function intersect at 90 degree. So they intersect at right angles, unless the derivative is 0, because if derivative is 0, it's going to disappear, so we cannot talk about anything. But otherwise, they intersect at 90 degree, or both, always. The curves intersect at 90 degree. This is something actually we can prove using Cauchy-Riemann equations. A really nice application of the Cauchy-Riemann. We learn in calculus that the gradient vector, which is defined as the component as the partial derivative of the function of u, is normal to the level curves of u. Similarly, the gradient vector that you define as the partial derivative of v is normal to the level curves of v. So that means if you have the curve, the gradient vector is normal to that curve. So what we're going to do now, we're going to look at the angle between the gradient vectors. To do that, what we're going to do, we're going to look at the scalar product. That's the way to do it. So look at the scalar product of the gradient vectors, which is defined as the you're going to multiply the corresponding component and add them. So this is how we define the scalar product. Now what we're going to do, we're going to using the Cauchy-Riemann equations, we're going to replace this term by this, because that those two are equal, And also we can replace the second one by this. This is using the Cauchy-Riemann equations. And you can see that this is going to give you 0. That means those two vectors are perpendicular to each other. So the angle between the two is 90 degrees because we know that they are not non-zero in general. That means the angle, because you can remember in the scalar product there's a cosine theta angle. So that means the cosine theta is 0. Cosine theta 0 means theta is 90 degree. So that means you can see that the level curves of conjugate pairs or the harmonic conjugate are at intersect at 90 degree. So you can see that if the gradient vectors are non-zero, then they should be perpendicular to each other. So in other words, in using technical terms, you can see that the level curves intersect at right angles. So sometimes we call they are the conjugate harmonic are orthogonal. That's like a term we use, orthogonal, instead of perpendicular. So let's try to do one last problem. So what it says that solve the Laplace equation. Solve the Laplace equation with phi equal 3 on the outer circle and phi equals 7 on the inner circle. So there are two circles. In the outer circle, which is 3, in the inner circle, which is 7. So in the context of complex analysis, what we are trying to do is we need to find a harmonic function because Laplace equation is a harmonic function that takes the value 3 on the curve x squared plus y squared equals 6x and the value 7 on the curve x squared plus y squared equals 4x. So that's how you can see through complex analysis. So if you look at the situation, this is what you get. So you get a phi equal 3 on the outer one, phi equals 7 on the inner one. And we also see that the function, the circle actually you can write in this form. So you can isolate 6, you can write this one as x equal so you can write as 6 exactly. You can divide and you can write this one as x over x squared plus y squared equals 6. You can do the same thing with the other one too. And you can see that actually this x over x squared plus y squared is a real part of the analytic function fc equal 1 over z. That's something that happen. If you try to simplify this using x and y multiplied by the conjugate, this is what you get as a real part. And you can see which is an analytic function everywhere except 0 because it's 1 over z. You cannot divide by 0. So thus the boundary curves are the level curves of a harmonic function. So that's the boundary curves because we know that that's the harmonic function because the fc 1 over z is an analytic function. So the real part has to be harmonic. That's exactly what we are looking for. That's the connection here. Now what we do, we try to use the given information phi equal 3 and 7 to find. So what we do, we introduce this special function. So you can see that's the function we have here, but we put a and b in there. That's like a one way to modify this. Consider a general situation, and using the two given information, we try to find a and b. So you need to find a and b. So, but we know that phi equal 3 on this circle, but we know the circle you can write as is a 1 over 6 because if you solve for, if you divide, you can write this one as a 1 over 6. So we do that algebra. This is 1 over 6. So that means if this is equal to 1 over 6, you can the function value is 3. And you can do the same thing with the other circle. This is going to give 1 over 4. And the function value is 7. Now what we do, you can see there are two unknown. you can solve them, and when you solve, you get a equal 48 and b equal -5. So that's exactly the uh, unknowns that we are looking for. So we can say that Cxy 48x over x squared plus y squared equal -5 solves the given boundary value problem, because the boundaries are given. So you can see it's a boundary value problem. So now you can try these problems as practice problems. So in the first one, they say find the harmonic conjugate of the function below so that u plus iv is analytic. In some problems, u is given, the real part is given. In some of other ones, the imaginary part is given. And you know that it does not really matter. The only thing is how you write it. And if you cannot do it, because there may be something that you cannot do, because you know that it has to be harmonic. So you check whether it's a harmonic function first, whether it satisfies the Laplace equation. If it not, then you cannot find it. And then also you can try these problems. So the question is directly asking, can there be an analytic function whose real or imaginary, depending on what you are given. So you have v and u. Real or imaginary part is given below. So you can try this. So we did a similar problem before, and also as the last problem, we do a little application problem here. So the first one says that find a function phi xy that is harmonic in the region of the right half plane between the curves so we have two hyperbolas, and takes the value 5 and 9. So this problem is similar to the last problem. And also let's do this one to solve the Laplace equation for the function phi in the region bounded by two circles and takes the value 1 and 2. So you can try these problems as practice problems.